So my talk will be, actually the connections with Poisson geometry are a little bit undeveloped. So most of the talk will be potentially applicable to Poisson geometry, and the link with Poisson geometry will occur in the later part with some discussion of coisotropic subspaces. That latter part is joint work with Jonathan Laurent, who's a student at, in Zurich at ETH, who's been visiting Berkeley since the first of the year, working on a master's thesis. And most of the work is joint with David, and some of it, well, the part I'll talk about in particular appears in a joint paper which we have posted on the archive some time ago. And David's part of the talk will be a work that's still a little bit in progress. So something that some of you know I've been interested in for a very long time is the problem of quantizing, that is to say, going somehow from symplectic geometry or Poisson geometry to some kind of linear algebra, not just isomorphisms, which is the theory of geometric quantization, say, but general canonical relations, Lagrangian submanifolds of products. And there are various reasons for wanting to do this sort of thing, solving PDEs, traces of the representations that you get by geometric quantization, and so on. And this suggests that whereas for diffeomorphisms you want a representation of some group, here what you have is rather a category of canonical relations between possibly different symplectic manifolds, and you want to somehow functorially quantize this to some kind of category in linear algebra or linear analysis. Problem with this is that composition is not always so good. So if we have a, maybe I'll start on this board. Can you see this board from over there? So if you have a, so what do I mean? So if you have a composition like this, then the composition comes about by looking at the pairs x1, x2 in L2, and then looking at pairs x0 with the same x1 in the second place in L1, and then saying that whenever there is such an array, then x0, x2 is in the composition. So it's useful when you want to see what kind of object the composition is to think of this as taking L1 cross L2. All this is going to take place in x0 cross x1 bar being the x1 with the symplectic structure reversed, cross x1 cross x2 bar, intersecting this with the things of this form where the middle component matches. I'll write delta 1 for the diagonal in x1 cross x2 bar, and then projecting this into along this factor here into x0 cross x2 bar. Now, if we want to work with something for example, embedded Lagrangian submanifolds here, then two things can go wrong. First of all, this intersection can be a bad object. It might not be a manifold. And even if it is, this projection might have some kind of singularities. Now, if this intersection is transversal, then it immerses in here. So that's not so bad. And in other words, because of the symplectic linear algebra, there's a relation between these two things that can go wrong. But still, one needs both things to go right. So we'll say that the pair L1, L2, well, a term used by Wehrheim and Woodward is embedded for such a pair because this intersection is embedded in here. I'm going to put it in a more general context and I will call such a pair congenial, friendly. And so, okay, so this is the problem is that not all pairs are congenial, so we don't really have a category for which these are the morphisms. Another thing I want to observe here that kind of fits with the last part of the talk is that this is a product of symplectic factors and a Lagrangian in here, so it's a coisotropic submanifold of this big product, and this is basically symplectic reduction. The delta one direction is exactly the characteristics of the induced form here, and this is the quotient. So this is a standard thing one does. You take a Lagrangian, intersect it with a coisotropic, and project to the reduced space. And that may or may not be given a good manifold. Incidentally, we can think of this itself as a composition. We can go from the point to x0 cross x1 cross x1 bar cross x2 by L1 cross L2, which is a submanifold of this cross the point with the symplectic structure reversed. And then from there down to x0 cross x2 bar by the relation which takes all the pairs here with the middle elements equal and forgets about that element. And this turns out to be a Lagrangian submanifold in the product of 6 factors here. So composition is itself a kind of composition of relations, and all the things that go wrong or can go wrong here are exactly the things that can go wrong with this composition here. Okay. So things can be very complicated here because of intersections can't be manifolds and so on. Things appear to simplify if you let everything be linear. So I'll call this, I'll start with the category first, symplectic relations, by which I mean Lagrangian submanifolds. It's not yet a category, except I'll use this to mean all relations among symplectic manifolds. And then it is a category. We just do this, and we get some kind of subset here. It turns out to be much better, or easier, not better, because it's necessary to deal with this, to work with symplectic linear relations in which these x's are symplectic vector spaces and the l's are linear Lagrangian subspaces, so half-dimensional spaces on which the form vanishes. And now this really is a category because the two defects, the degree to which this is not transversal and the degree to which this is not an embedding, cancel out, and one always gets a Lagrangian subspace here. However, this has problems also in that if you think of the Lagrangians in here as elements of a Grassmann manifold, then this composition operation, which takes L1 comma L2 to this composition, is not a continuous operation. It's not smooth, but it's not even continuous. This problem, this discontinuity, which occurs exactly at the places where this fails to be a transversal intersection, this discontinuity also reflects in some bad behavior when you want to try to do some kind of quantization. So the idea of quantization is somehow we assign to each symplectic vector space a Hilbert space or some other linear space, like a space of distributions. I'll still call it H. And the idea should be that to every L here, one should assign an operator from here to here. And this picture of it sort of tells you what happens in terms of like kernels of operators. If you have a function of the 0th and first variable and another of the 1 and 2 variables, you first get a function of 4 variables, you set the two things in the middle, and this corresponds to integration over that middle variable. So this part of the operation is fine. Integration of functions over the middle variable may or may not work very well, depending on what you're integrating. And again, somehow having a good composition here leads to good behavior for this operation here. Now, in the linear case, this is more or less completely worked out, was in about, I think, 1978 or so by Victor Gilliman and Shlomo Sternberg. And they showed that the natural association of a Hilbert space to a symplectic vector space allows one to attach a well-defined operator to every linear symplectic transformation, at least up to a constant, a scalar factor. And composition works very well, except exactly in the cases where this intersection is not transversal. And then in their paper, they simply say, well, it doesn't work. We won't even try. So that's bothered me for, what is it now, going on 30 years. And I have finally, somehow with the help of Shlomo, with the help of Shlomo, found a kind of solution. And then it got even better when David came to Berkeley and we started working together on this derived picture. So I'll come back to that. I'll come back to that in a minute. But I just want to give an example of how this composition can go bad. If we look at this diagram of symplectic manifolds, or symplectic vector spaces even, the 0 space, the plane in this space, and I'll let L1 and L2 be the same thing, namely the vertical. So I'll think of this as the cotangent bundle of R. Then the quantization of the vertical as a relation from a point to here, well, we quantize this. This becomes the complex numbers. This becomes some kind of space, like a space of distributions on R, and then we go back to the complex numbers. Then this map here essentially takes a constant to that constant times a delta function, which is, what else could it be if it's concentrated at the origin? This one is the dual of that, which takes any function and takes its inner product with the delta function to get a number, and that essentially means evaluated at 0. So if we want to compose these two things, then the result is you take a constant, you take that constant times the delta function, and you evaluate it at 0. But you can't evaluate the delta function at 0. You get some kind of infinity. It's not a complex number. And so that's an example, and in some sense it's the most general example of what goes wrong when you try to quantize these incongenial, or the word I looked at, I thought it was incongenial, it turns out to be uncongenial compositions. So there have been a couple of approaches to dealing with this kind of problem, and the one which I've followed for a long time is that of, well, a long time meaning, I don't know now, 4 or 5 years, by Katrin Wehrheim and Chris Woodward, which is in terms of categories, and a very simple operation that makes everything work nicely, at least formally, on the classical side. But I wasn't able to get anywhere on the quantum side until I was going through the files in my office a couple of years ago in preparation for starting to share my office with Hongxi Wu. And I was going through all the old correspondence. I found a 1982 letter to me from Shlomo Sternberg, which was written on the beaches of the Red Sea, I think. And so he said he did, when I asked him about it later, he said he didn't have a copy of it. And in it, he actually proposed a solution to this bad quantization. And he said that it was proposed in a lecture by Ofer Gaber at a seminar that he'd been running in Jerusalem. So, of course, I immediately wrote to him, and he said, the letter ended by saying that this was going to be contained in an upcoming work with Victor Gilliman. So I wrote to Shlomo, and I said, I'm not sure I've ever seen that work. Could you please tell me where it is? And he said, well, we never actually did it. We intended to, but good intentions, well. And I'll tell you, so roughly the idea is instead of looking at vectors in Hilbert spaces, you look at modules over the algebra of operators on the Hilbert space. So this fits very well in what's called the theory of D modules. And then in this picture here, composition is done normally by a tensor product. But kind of borrowing an idea from algebraic geometry, due I think originally to Serre, rather than looking at just modules and tensor product, you have to look at complexes of modules and derived tensor product. Derived tensor product means torsion products and higher torsion products, and David will explain some of this in his talk. So in my talk today, I want to concentrate on this first approach, which doesn't get you the quantization, but at least it produces what turns out to be the right thing to quantize. And so the idea is to introduce what we'll call a selective category in which we distinguish certain morphisms as the good ones. So for example, in S-rel, we have all relations among symplectic manifolds, but only those which are given by a smooth Lagrangian submanifold embedded, properly embedded, will be considered what I will call, in this more abstract formulation, suave morphisms. Originally, I was calling them smooth, but that suggests too much. So a sort of smooth character is sometimes called suave. And among the suave morphisms, we distinguish certain composable pairs as congenial. And then to begin, we put very simple axioms. For example, that the identity morphisms are all suave. The composition of a congenial pair of suave morphisms is again suave. And finally, a kind of associativity is if we have three morphisms which are composable and suave, if this pair is congenial, which I'll indicate by putting a dot in here, and then after you've got this composition, this is also congenial, then it's also congenial in the other direction, and vice versa. That, for a long time, I didn't even find a place to use that, but it seems to be useful. Another thing is that it seems to be useful to say that if F is a suave isomorphism, then its inverse is also suave. And the pair that you get by composing them, some identity, this is always congenial. OK, so with just that bare minimum, we can define, if I have a selective category C, I can build out of it a category which I call WWC for Wehrheim and Woodward, in which we start with chains of, maybe this is Y, and this is the target X, chains of suave morphisms, congenial or not, I can compose those by concatenation, but that really isn't so interesting. But what is interesting is that if I allow a certain relation, that if I have somewhere along the path a congenial pair, then I am allowed to replace it by its actual composition. So I get a path that's one shorter. But I can also go in the opposite direction. I can take something in a path and factor it as a congenial product. So it's very easy to see that this is now a category. There's a functor to the original category, which you get by giving such a chain. You just form its composition in C. And that shows immediately that although you introduce these relations, you don't make things smaller. So if I have a single morphism, and even though I'm allowed to expand it and then contract it again, if I get back to a single morphism, it'll be the same one. So I don't lose any of the information of C, but I keep track of these good compositions. And of course, what I'll do in this case here, in actually both of these cases, is say that, well, in the linear case, which is going to be the subject of the rest of the talk, everything is suave, but the compositions are congenial only if there is only if this is a transversal intersection, which is actually equivalent to this intersection down here being an embedding by kind of symplectic duality. What Wehrheim and Woodward were doing was in symplectic topology, they were using this one, and they quantized things not by Hilbert spaces, but by actually other categories built from Lagrangian submanifolds, some version of the so-called Fukaya category. Now, in order to go further and say anything interesting, we need a further refinement of this thing. And there are actually three adjectives that we can put in front of selective category. We can say it's highly selective, and then we can also apply these general notions from category theory. So let me get rid of this. Let me just say it in a few words. Monoidal category means there's some kind of a product operation. And it acts both on functors and on objects. And in our cases, the operation will just be the Cartesian product. In some other applications, it's a tensor product. And in fact, in some sense, after quantization, you will get tensor products. Rigid means that there's some notion of duality, which you can is defined in a very concrete way. And you can look at it in my paper with David, for example, or any book on abelian categories, or any book that goes beyond the very beginnings of category theory. And we'll say we have a rigid monoidal selective category if these operations of dual and product are compatible with the selective structure, namely they preserve suavity and congeniality. Now, highly selective is something that's more particular to this story. For this, we distinguish two categories, subcategories of whatever our original category C was, and we'll indicate the morphisms this way and this way. These are somehow special at the target. These are special at the source. We'll call these reductions, so we simply pull out subcategories of reductions and co-reductions. same object so that all the identity morphisms are both reductions and co-reductions, with the property that if we have a composition like this, which is, I say it's decorated at the middle object, meaning either that this is a co-reduction or this is a reduction, then this is congenial. So these are actually subcategories of the suave morphisms. So for example, in this S-rel, remember a reduction is given by a relation from here to here, and we'll say it's a reduction if two things are true. First of all, it's surjective, and secondly, it's uniquely defined. That is to say, for anything in y, there's only one thing, at most one thing in x. So for a reduction, what you do is you pick out a subset of y, which is the domain, and you, so to speak, project that onto x. And if you're in a differential situation, then you want a smooth manifold here and a proper map to x. Now, if you, not necessarily proper, just a smooth manifold and a submersion to x. And these are just going to be the dual objects. Instead of there being onto x, they're going to be defined everywhere on y. And instead of being given by a single valued function, they're going to be injective. So that means every element of y gets mapped to some subset of x. And different elements of y go to disjoint subsets of x. Okay, so these are, this is the same thing in the linear case, although it's a lot easier to say what they are. Here, you take a coisotropic subspace of y and essentially project it onto its quotient by the characteristics. And here you just take the same thing, but in the opposite direction. Okay, so this is a definition of a highly selective category. And the nice thing about these is you can actually prove something which is very simple. If I have a diagram like this, in other words, it's what I call a WW morphism, then it's always equivalent, or in the WW category, you can do those moves to get it down to something with only one thing in the middle. And furthermore, this is a reduction, and this is a co-reduction. So it's not necessarily a congenial composition because it's decorated in the wrong places. But it's still a very special type of thing. And you should think of something like taking an arbitrary mapping and first taking the domain, mapping it onto the graph. So let this be the product of x cross y, and then project the product onto x. Well, that's not quite, you have to do something a little more complicated for relations. But it turns out that these categories here are, in fact, highly selective categories with the definitions I gave of reductions and co-reductions. Now, one thing that's interesting to do in any monoidal category is to look at morphisms from the unit object to itself. First of all, they form a monoid. The unit object is one where tensor product with it doesn't change anything, like the point in these categories here. So the morphisms form a monoid. There's an associated composition with an identity. And what's more, if you take the monoidal product of this with a morphism from y to x, you get another morphism from y to x. And this is compatible with the composition here, so that this whole category becomes a kind of monoid over the endomorphisms of the unit object. So I'll write 1 for the unit object from now on. And remember that it's a point it's a point in SREL, and it's the 0-dimensional vector space in SLREL. So it turns out that we can again, now we go back to this special particular category, SLREL, of linear canonical relations. We can actually prove something. We can prove that in WW of SLREL, the morphisms between two symplectic vector spaces, we'll always assume finite dimensional here, I didn't say that earlier, correspond to pairs LK, where L is a Lagrangian subspace of X cross Y bar, which is a usual morphism in the original category, and K is a non-negative integer. And we'll call L, this L the shadow of the morphism here, and K will be called the excess, which is a term borrowed from derived geometry. And it actually corresponds to that sort of thing. So I've described given a complete description of this category, and it even describes a module structure. If you take a composition of one of these things with a morphism of the unit object, which just corresponds to one of these non-negative integers, you just add the integers. But the more general composition law is this, that if I take LK and compose it with L prime, K prime, the result is, the first part is what you think it should be. It's just the ordinary composition, congenial or not. And then you add the excesses. But then you add, there can be more excess, which is the excess of the composition of L and L prime, where epsilon of L and L prime is equal to the dimension of L cross L prime intersected with the kernel of the projection, which I erased. Remember that what we do is we intersect this with X cross the diagonal cross Y, or diagonal across the third object, and then I project it by eliminating the middle object, and this is the kernel of that projection. So that's the excess of a pair. And so we have a very complete description of this category in which the nice compositions stay the way they were, and we keep track of how bad the bad ones were. And it turns out this is the right category to quantize. Furthermore, there's actually a topology on this category which which makes the composition continuous. It's a, I think I might come back to it if there's time. I call it the Sabot topology because it's inspired by work of Christophe Sabot, in which he makes composition continuous by making it multi-valued, by taking the graph of the composition on the nice parts and taking its closure. And he uses this to study some dynamics of compositions, which then get applied to random walks on fractals. It's wonderful to see these ideas used there. Okay, so as I said, in David's talk, we'll see how this thing comes about in another natural way without the necessity of actually doing the classification that we do here. And the Sabot topology also arises in a natural way. Okay, so I think I want to go on to the coisotropic story. So this is where the subject stood about several months ago when I realized I have to give a talk on Poisson geometry. And I've been spending most of my time on this subject. So I thought, well, how would you do this for Poisson geometry? Well, we should look at Poisson manifolds and coisotropic submanifolds of products, which are in particular the graphs of Poisson maps. And before doing that, we should look at coisotropics in the linear case. So PL-rel, maybe Poisson linear relations between Poisson vector spaces. So, I mean, this is sort of a subcategory. It's conceivable that you might get more identifications if you allow yourself to factor things as products where you introduce some Poisson vector spaces and coisotropic rather than Lagrangian relations. I'm pretty sure that's not the case. So this really, the WW of this is a subcategory of this. Now, also subcategory of this is what you get by looking at zero Poisson structure, just linear spaces with zero Poisson structure for which all subspaces are coisotropic. And you see by looking a little bit at this that you want to, well, what happens there is that if I have a diagram of vector spaces and relations, I'll call them A and B for now. Remember what we do, we form the intersection of A cross B with X cross the diagonal of Y cross Z, and then we project it into X cross Z. And so, as I said, there are two things that can go wrong. This can fail to be transversal. In other words, the direct sum of this space and this might not be the entire X cross Y cross Y cross Z. So we measure that discrepancy by the difference in dimensions of those two spaces, or better, the dimension of the quotient of the full product by the direct sum of those two spaces. On the other hand, we have the other thing, which is the kernel of this projection, and the dimension of that is called the excess. So we have a defect and an excess, and it's natural to say that something is going to be congenial if and only if its defect and its excess are zero. In particular, this allows us to get rigidity. When you have relations, you can get relations of the duals, and when you form the dual of a relation, the excess of one becomes the defect of the other one. Coefficients are constant. Yeah, Poisson vector space, not a Lie Poisson vector space. Just constant. Yeah, exactly. And so if that subspace which is symplectic is zero, then you just get this linear algebra. But even for general coisotropics, there are these two. There's two invariants which are now independent: the defect and the excess. Now it turns out, in this case, what one should really look at is the morphism from the coisotropic morphism. Okay, let me skip it, go ahead further. So that's the one kind of sort of trivial case of Poisson vector spaces. The other extreme case is symplectic vector spaces. And there's a hope that by understanding both of those special cases, you can put them together for the general case with a little more extra work for the interaction between the two. And so up to now, Jonathan Laurent and I have been concentrating on this case where the vector spaces are still symplectic, but the relations can be coisotropic rather than just Lagrangian. Okay, so from here, one is naturally led to trying to understand the endomorphisms of the unit object. And I'll talk about that for a while now. So, new what?
Did you tell us whether you're introducing new relations?
Let me say, ask me again. I have to tell you what's, so these are the congenial things. The reductions and co-reductions are more or less what they were before. And then we just do this WW construction of looking at chains of morphisms and allowing us to make the congenial compositions. But Nate, I don't think that was your question. Or was it?
So you mentioned about introducing Poisson case raises the question of whether you're introducing more relations.
Whether you're introducing more relations among morphisms, among these chains of morphisms, if they were in the original category. And as I said, I don't think you do, but I'm not 100% sure of that. I have a feeling you can't get rid of the, mainly because the excess is still part of the story here, you can't get rid of this K here when you look at the subcategory of things given by Lagrangians. Okay, so what is a, remember 1 is the zero-dimensional vector space. What is a WW morphism from 1 to 1? Well, by that theorem that says you can boil everything down to 2 steps, it looks like this, where these are simply both coisotropic subspaces of X. And we want to classify these things up to those WW moves, which would allow us to factor one of these things, factor again, compress in a different way, factor, compress, and so on. Well, essentially what we have here is a pair of coisotropic subspaces. Now, if they were Lagrangian subspaces, we know immediately that the invariants of a pair of Lagrangian subspaces are the dimension of the full space and the excess, meaning the intersection of those two Lagrangian subspaces. That is, the excess of this is always actually the intersection of A and B. Okay. Now, it's more complicated in the coisotropic case. But let me see, why are we interested in classifying them up to isomorphism? Well, first of all, if classifying up to isomorphism, it turns out that if I have an isomorphic pair, then by doing the right sort of, you factor this into, well, you factor this into this times this, and then you factor again, and you get a WW moves which take you from here to here. So isomorphic morphisms are always the same in the WW category. Now, the other thing that's true is that if A and B are transversal Lagrangians in X, then this is a congenial composition. And by taking the product of the monoidal product, which here means the Cartesian product, of an arbitrary thing like this with transversal ones, we get the same WW morphism. And what we've done is we haven't affected the intersection, but we've changed the dimension of the underlying space. So the only thing that remains invariant here is the dimension of the underlying space here, of the intersection, A intersect B. And that tells us that the morphisms from here to here in the Lagrangian case are just classified by their excesses. But now what about the coisotropic case? Well, we succeeded in doing the classification up to isomorphism, and we know a little bit about the relation between that and the classification up to these WW equivalences, but we're not sure about the whole story. So let me talk about the equivalences. By the way, the equivalences are also interesting. If you go back to the original problem of looking at, let's say, symplectic vector spaces and canonical relations, then we can try to classify them up to isomorphism. But what's even more interesting is the case where you have a canonical relation, a Lagrangian subspace of X cross X bar, and you want to classify it up to conjugacy, where you use the same diffeomorphism, same isomorphism on both ends of this diagram. So if we were dealing with mappings, like, well, linear mappings, then that's something like Jordan canonical form. In the case of symplectic linear mappings, that's a classification due to a bunch of people, Cushman, for example, and most recently Jean Gut. So let's try to do this for canonical, or for still canonical relations. Well, there's a result of Tulchev that says that every morphism like this can be factored. Well, essentially, it's a reduction and a co-reduction, but what... Okay, I'm not finished. And this is even true when X and the outside spaces are not the same, and an isomorphism in the middle. In other words, we have a coisotropic, well, let's say the general case, first of all. Any canonical relation from Y to X comes about by first reducing by a coisotropic subspace B here, and reducing this by an A, and then taking an isomorphism between those two reduced spaces. Okay, so now let's go back to the case where this is the same space, X. Then if you want to classify these things up to isomorphism, the first natural thing to do is to classify the pairs A, B up to isomorphism. So that's what I'll describe to you. And Jonathan has gone much further in actually classifying the relations and not just the pairs consisting of their domain B and their range A. Okay, so for the classification, I will draw a picture. So if we were just doing, first let's assume that we were just doing it for linear spaces. Then I'm going to without any symplectic structure. So I'll think of this oval here as, let me make it a little different so that you're not tempted to think that they were the same. I'll call this space A, and the one going this way, B. And I will use the convention that intersections really represent intersections of spaces. Disjoint things represent vector spaces. Well, they can't be disjoint because they always contain 0, but they'll be complementary. And unions also represent direct sums. So for example, here we can put the intersection of A intersect B. And then we can choose complements of A intersect B in the two spaces. And so I'll call the complements E1 and E2. So E1, actually, this is also part of E1. I've drawn this diagram because I want to go symplectic in a minute, and this is good preparation. So you can see essentially that the invariants here are the dimension of A intersect B and the dimensions of A and B. And one more, which is the stuff that's not contained in here. I could call that J. So there are 4 numerical invariants for a pair of intersecting subspaces in a vector space. But when when it comes down to classifying this WW in the WW land, the only things that remain are A intersect B and J, which are the defect and the excess. Now, when we go to the world of symplectic geometry, there's a new feature, which is that a coisotropic subspace contains an isotropic subspace inside it, which is its orthogonal, if you want, or its characteristic subspace. So in here, there'll be a smaller space, which I'll call A upper omega, and here there'll be a smaller space, B upper omega. And so now we have to add these to the diagram. So now this space here, which I'll shade like that, is A omega. And this one here, which I'll shade this way, is B omega. So we now get a much finer decomposition. In the middle here is the intersection of the characteristic subspaces, which I'll call I. The sort of outer ears of this diagram stay the same, but now we also get a space here, which is in both A and B, but is characteristic for neither one. And that turns out to be a symplectic subspace. This is symplectic. And finally, there are, so now these spaces are no longer, now this part is different from this because what I called E2 is characteristic for A, and this part is the part of A, this is a part of B that's not characteristic for A. This is the part of A that's not characteristic for B, and we call these G2 and H2. And there are 2 more spaces in here. There are these things that look like squares in this diagram that I'll call G1 and H1. So associated to this pair, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 different subspaces. So it looks like there might be 9 invariants. But in fact, duality shows that the things that I marked with the same letter in different numbers are naturally, they're symplectically dual, well, they're symplectically orthogonal to one another, And they're in natural duality via the symplectic form. So for example, E1 plus E2, I'll use the cross. This is a symplectic subspace in which E1 and E2 form a Lagrangian splitting. The same is true with I, which is A. J is the big space modulo A plus B, and this is A omega intersect B omega, and those are symplectically, those are dual, naturally dual to one another, again. So we have, instead of writing the products here, I will write I comma J. It's a Lagrangian pair in their direct sum. Then we have E1, E2. F1, I'm sorry, G1, G2, H1, H2, and finally F, which is symplectic and doesn't have a natural Lagrangian splitting. So there are really only 5 different numbers here. And it turns out that those 5 are a complete set of invariants. So these give symplectic vector spaces. The dimensions of these spaces I'll call N1 through N5. And so what we're saying is that any symplectic vector space with a pair of coisotropic subspaces can be written as a direct sum of 5 spaces. In the first one, we have a pair of transversal Lagrangian subspaces as our coisotropic pair. In the second one, we actually have the same subspace here that's the same Lagrangian, because it's only the I that contributes to A and B. So here that's the same Lagrangian twice. Here they're complementary Lagrangians. Here one is Lagrangian and the other is the whole space. Here it's the other way around, and here both coisotropics are the whole space. And the dimensions of these form a decomposition. It's also possible to write these in terms of more computable invariants that are much easier to understand. And the last question, which I still don't know, is how are these related to WW invariants? Because there's the analog of adding a Lagrangian pair, which is a trivial morphism here. And that turns out to change N2. So N2 gets lost in the WW classification. Some other things, there's the excess and the defect are combinations, 2 combinations of these that are surely invariants, but it's not yet clear whether there are other things you can do with the WW moves to reduce that number of 4 invariants to either 3 or 2. So that's work in progress. Anybody's comments are very welcome. Thank you. Well, that's a good question, which you're not the first person to ask me. I don't know much about model categories, but I was stimulated to learn about them. And it doesn't really fit that picture. There isn't a model category structure here. In particular, in model categories, there's no, one of the essential things here is this notion of distinguishing the suave morphisms. Now, there might be some way of getting something like model category structure with something extra in it, but I haven't really succeeded in doing anything useful. There is Somebody else pointed out that there's a construction in K-theory due to Waldhausen, which very much resembles the proof of this theorem that you can take a long chain and break it into two pieces. There's also something like that by Whitehead in simple homotopy theory. But there doesn't seem to be any way of reducing any one of those theorems to the other ones.
At some point you just mentioned that this technique of quantization, because that's the point of it, is a different way of quantization than another technique using higher categories. And
Yeah, no, I don't have, I mean, the quantization of this, which David will describe, really does use higher categories.
okay.
And that's the only one we have at this point.